univariate Gaussian distribution. How many of you have seen this expression before? I'm hoping to a full show of hands. It's a way of measuring the uncertainty for a variable that is continuous between minus infinity and infinity, defined on the real line. And the multivariate distribution, we probably have all seen it, is this sort of bell curve, which is defined over the domain of a random variable x. And a random variable is just a variable that's measuring some quantity that is uncertain. So think of, for example, temperature is a random variable, pressure is a random variable. Most of the concepts that we talk about usually in real life are actually random variables. There's no such a thing as temperature. Temperature is just a statistical estimate of how the molecules are colliding in this room and dissipating heat. I'm not going to go into the details of what is a random variable, what is a probability distribution. That sort of thing, I'm going to assume that you guys have done a basic course. And even if you haven't, you'll see that you'll pick it up easy in this course. I think most of the math I will try to, certainly in 340, I went over all these concepts. So if you feel like you're a bit shaky, you can't remember your linear algebra, you can't remember your probability, please watch the 340 videos from last term. They're all in YouTube. Just sit back, get popcorn, and you'll basically learn everything that you need. Okay? I'm going to introduce everything in this course, but I might go quickly over it. Like I won't go into it. You know, in 340, I have a whole term to introduce linear algebra and probability and so on. So obviously, I can't afford to have half a term to do that in a graduate class. Okay, so the Gaussian distribution is centered at the parameter mu, which in this case is just a scalar because we have a univariate distribution. It's a bell curve. Its width is controlled by this parameter sigma. The bigger sigma, the wider it is. Sigma is called the standard deviation. Sigma squared is called the variance. Mu is called the expected value or the mean. And what's the area under this curve equal to? 1. It's a probability distribution. Okay, so the integral of e to the minus 1 over 2 sigma squared x minus mu squared. If I integrate this over x, what should I get?
Square root of 2 pi sigma squared.
Exactly. Okay, does everyone see that? The integral is the area under the curve. In other words, the integral of p of x dx must be equal to 1 from minus infinity to infinity. And so if I use the expression for p of x, I realize that 1 over the square root of 2 pi sigma squared is just a normalizing constant. It doesn't depend on x, so I just basically move it to the other side. Okay. And that actually turns out to be a very useful fact. If you know the normalizing constant of a distribution, is something that we will exploit in Bayesian, a different form of learning that I'll introduce in the next class called Bayesian learning. We'll exploit that fact to be able to do, to be able to obtain estimates of unknown quantities. Okay. Now, if we have a Gaussian distribution, we can also draw samples. Now, what I mean by drawing samples? What I mean by drawing samples is that if this is my Gaussian, I can call a random number generator and produce samples. And then I will get most samples in the middle and a few perhaps in the tails, but most of my samples will be in the middle. Okay? When I write X simulated or sampled or generated from a Gaussian distribution with mean mu and variance sigma squared, I'm saying that X is a candidate from that distribution. I've simulated it. Okay? Now, how do we simulate in a computer? How do we simulate Gaussian variables in a computer? Has anyone looked into that?
Rand-n function.
Pardon?
Rand-n function in MATLAB.
The rand-n function in MATLAB. Okay, that's definitely one that I've used millions of times. Now, how does rand-n work? What's the Python one?
The summation of many random.
Rand? Okay. Sorry?
Summation of many random variables become Gaussian random, I guess.
Okay. Something we're going to talk about today. There's something called the central limit theorem. That if you have random variables, as the n goes to infinity, they sort of become Gaussian. You might not have the time to wait till infinity, though, in your personal computer. Rand-n is a lot faster than infinity.
Binomial
Pardon?
binomial distribution when n goes to infinity.
So rand-n is very fast. I say to MATLAB or Python, give me 100 variables that have mean 2 and variance 1. And it's just like this, right? It's really fast. So you can't be doing asymptotic calculations in the limit. It's doing something else. Okay, let's take a step back. How does a computer produce random numbers? Any random numbers?
There are some algorithms that produce random numbers, and they start from a seed. And I think if you fix the seed, it always produces the same sequence of random numbers.
Exactly. You take actually nonlinear dynamical system and you simulate. And this nonlinear dynamical system is varied enough that if you pick the seed, that is, if you pick the initial conditions of if you choose the seed, you're choosing the initial condition of that nonlinear dynamical system, you'll always get the same random numbers. That's why we sometimes freeze the seed to get the same random numbers. But essentially, drawing random numbers is just taking a process that might depend, say, on the time in your computer, a deterministic process, and then picking these numbers and then assuming that they're actually random. They're actually pseudo-random. Computers are pseudo-random devices. They don't actually give you random numbers. Now, they're good enough that we don't worry about it, but there are some very sort of fancy applications of simulation where the random numbers that computers produce are not good enough. And so we get into trouble. And in those cases, physicists go through great extent toward getting random numbers. They will take devices that measure the gamma rays, impinging on the atmosphere, and they create this box, which is a random number generator that uses these gamma rays, and they sell it to you for like $100,000. Okay, so producing random numbers is actually quite an art, and it's a difficult engineering piece of work. In computers, there's been a lot of work on pseudo-random number generators in order to produce these random numbers. Now, it turns out that for a lot of machine learning algorithms, we will use this process of generating random numbers. But we'll not just generate them from uniform distributions, but from all sorts of distributions. And that process of generating from the distribution is essentially the process of imagining. Okay, or the process of predicting. Who are the humans that are best at imagining things?
Artists.
Artists, children. Children are always in the special worlds. You know, they're inventing little things. There comes the prince, and the prince kills the princess, and she, like, the dragon flies over, and they always have these little worlds, and they're always being imagined. That's because they're the ones that are learning the most. They're learning causality, they're learning relations in the world. Being able to imagine is essential to intelligence. And we humans are particularly good at imagination, at simulating scenarios in the world. Most of us live our lives in these scenarios. And, you know, life is what goes by when you're not thinking about it, as many have said. But we're always simulating what's going to happen in the future. You know, how will this class end up? You know, what kind of job will I get? Maybe I will, I don't know, maybe she'll like me and go out on a date or whatever. We live on these simulated scenarios, which are essentially our hopes and so on. They're also our regrets because we also simulate the past. What would it have been if I had done that? If I hadn't been a total douchebag with her, would she still be with me? That sort of thing. And that's actually very useful too, because that allows us to deal with what scientists call more dryly counterfactuals. And that's going to play a big role in learning causality at the end of the course. Because you only learn what causes what if you can think of what would have happened had I not done this but had done something different. Being able to do that simulation in your head is essentially doing an experimentation, doing actions in your head. We humans keep acting on the world without actually doing anything. We just run the scenarios in our head. And that's essential in order to understand the world and to learn. So simulating is sort of very important. And a lot of the algorithms that we will learn later for learning, and this is something I don't do in 340 at all, so for the 340 guys is new. Simulation will be critical to being able to do learning. Okay, so computers have the pseudo-random number generators that allow them to draw numbers from uniform distributions. Now, a uniform distribution is just something that will look like this. Okay, it has uniform height, and hence uniform. Now, when we draw samples from a uniform distribution, we will expect that those samples are sort of uniformly distributed, so that when you take a histogram of those samples, you sort of get back that box, that uniform box. If I were to take a histogram of these samples, I would probably get a big box here, another box here, maybe a small box here, and then this would be at 0. And essentially, this is the process of Monte Carlo. You histogram samples, and then this histogram, the more samples I have, the better that histogram will approximate the actual density, the actual distribution. Now, the way we generate this in a computer is as follows. We don't know how to generate from a Gaussian. We do have an expression for the cumulative distribution of a Gaussian. So if we have a Gaussian distribution, P of x as a function of x, we can also integrate, we can also consider the sum as we move from the left of the areas, and we will get a curve that looks like this. And this is called a cumulative. It starts at 0 and it goes all the way up to 1 because it's the area. So it's the area under the curve as we move this point x naught from left to right. Okay? So that's our cumulative distribution. So what we can do now is the following trick. And this is what I think MATLAB does this. You have the cumulative of a Gaussian, which asymptotes at 1. And then on the image, on the y-axis, we do the following. We put a uniform distribution there. And then what we do is we draw a random number according to that uniform distribution. That's using the pseudo-random generator that gives us uniform numbers. We project that number onto the line. And then at the point of intersection, we read off the sample. Now what's going to happen is, if you think about it and you look at, you take several samples, is that you'll end up with more samples here and less in the tails. So you end up with samples. So when you do the projections, you get something that will look like this, where most of the samples are around the mean. I should have said a point of a half is where the mean is, right? Because a Gaussian is symmetric. So most of the samples will be about the mean and very few samples toward the tails. And the tails of a Gaussian, because a Gaussian is an exponential function, those tails go down to 0 at an exponential rate. So they vanish very quickly. So the probability of getting a sample in the tails away from the mean vanishes at an exponential rate. Okay, so that's how a computer then generates Gaussian random numbers. That's how RAND-N works. So RAND gives you the uniform random numbers. Now we know how to generate Gaussian random numbers. Now we can move on. Most of machine learning is with many variables, not just with one variable. One variable is like first year, second year undergrad. Everything we do is with many variables. With two variables, for illustration purposes, your samples, again, will sort of capture where most, if you were to draw samples from this 2D Gaussian distribution, which you call technically bivariate, you would end up with a cloud of samples in the middle and less samples in the tails. Now the bivariate distribution, if you look at it from the top, can have many different shapes. You could have a bivariate distribution like this, that is perfect, that's circular. You could have one where the variables, say, x1 and x2 are positively correlated, or something like this, where they're negatively correlated. But most of the samples would be in the middle. And beyond a certain point, the probability of getting a sample is very low. The multivariate Gaussian distribution is just a generalization. So it's a bell shape in n dimensions. We can no longer visualize it, but the expression is still the same as what the expression would be for a Gaussian. And it's essentially given by this formula. Let's parse this formula. So this is a distribution in terms of y. So y is the random variable, or random vector in this case, because y is a vector in n dimensions. Mu is a vector of n dimensions, and mu essentially is again the center. So in the 2D case, this would be mu1, and this other coordinate of the center would be mu2. So the mu's give you the center. And then the matrix sigma describes the shape of the Bell function. So in the 2D case, we would have sigma being equal to sigma 1, 1, sigma 1, 2, sigma 2, 1, and sigma 2, 2. sigma 1, 1, it's essentially the variance of this distribution along this axis. So if I were to look at the distribution, let's put an I here. If I look at it this way, I'm going to see a Gaussian. And if I look at it this way, I'm also seeing a Gaussian. So if I were to cut this on any direction, a bell, I would still get a bell in a lower dimensional space. Sigma 1, 1 looks at the width in the lower in the x direction. Sigma 2, 2 in the x2 direction. Or sorry, in this case I'm using the variable y, the y2 direction. And then this term here looks at the cross correlation. So let's look at some examples. If I have something that is sigma equal to 1, 1, 0, 0, my contour plots will look like this. They'll be circular. That's when the variables are independent. If I, on the other hand, have some correlation, so sigma being equal to, I don't know, 1, 1, 0.5, 0.5, and sigma is symmetric, so sigma 2, 1 is always sigma 1, 2. Then I would have something that would look more like this. Okay, so it would be an elongated Gaussian. And if they're anti-correlated, it would be in the opposite direction. So by changing sigma, I essentially get all these shapes here. These are just different shapes. So sigma and mu are just parameters. They typically will be unknown. Typically, I'm given points, and I try to learn the mu's and the sigmas. Okay? And we'll see an example today of how we do. We'll move on to do an example of how we learn the parameters of the Gaussian from data. All right, so let's continue playing a bit with the definition of the Gaussians. I know this is a bit dry, but it's really fundamental to know how Gaussians work in order to do machine learning with continuous variables. Now, I'm going to introduce a concept called independence. And somehow imagine that this is a circle. That was a poor design. So if you have two variables and they're independent, and I'm saying that both variables are Gaussian, one variable has mean mu1 and variance sigma squared, the other variable has mean mu2 and it has the same variance, which is sigma squared, then the joint of two independent variables, p of x1 and x2, is the product of the two distributions. That's what independence means. Okay? Independence means that you can break the probability as the product of the individual probabilities. And if we do this calculation and we write this as 2 pi sigma squared to the minus a half, and then we write the expression for these probabilities, I can group terms and write this as 2 pi sigma squared to the minus 2 over 2. I multiply the constant factors outside, and then I write this as e to the minus, and I'm going to write this, try to take this to vector notation, and I'm going to write this as e to the minus a half x1 minus mu1, and I'm going to try to transpose it because it's a scalar, it's the same, and then sigma squared minus 1 x2 minus mu 2 plus, x1 minus mu 1 plus x2 minus mu 2 Where I'm going with this derivation is I'm trying to go from the univariate distributions to a multivariate to the bivariate Gaussian distribution so that you can see how you map from one to the other. And so this is equal to 2 pi sigma squared minus to the power minus 1. And then I can rewrite this as e to the minus a half times x minus mu 1 So I'm going to create a vector here which has mu 1 and mu 2. I'm going to put brackets to separate them. Okay. So what I've sorry, go ahead.
Why is the power is minus 2 for the sigma squared in the second term, entire time?
In the power minus 2, you mean of this guy?
Yeah, the sigma squared in the second term is minus 2.
Oh, that should be minus 1, sorry. Thank you. I had already done it. So basically the way I've written it now, you can see that it's just a vector which has the terms x minus the mean times the covariance in this case, which is just this matrix here. So this guy here now is essentially sigma. So if we compare it to the expression of a Gaussian, that matrix that has the sigma squares is just a sigma, and then there's a vector y. In this case, I'm using the symbol x, and then there's a vector, and I should actually use indices here. And then there is a vector of the means, mu1 and mu2. So that gives us the mapping from univariate to multivariate. The other thing that we see is that if variables are independent, the covariance is diagonal. There will be zeros off the diagonal. Zeros in the off diagonal of a Gaussian just means that you have independence. There's a question here.
The previous slide had the absolute value of the matrix. I was just wondering if that was possible.
Oh, yes. So we can also, so here we have not the absolute value, but the determinant of a matrix. So the determinant is the product of eigenvalues, or the usual form of the determinant. So I haven't shown that part yet, but it's kind of, if sigma, if we let sigma be equal to sigma squared, like this, or as I often like to write it, sigma squared times the identity matrix, where the identity matrix is a matrix with ones in the diagonal and zeros elsewhere. Then the determinant of the matrix is just sigma to the power 4 in this case. Just using the standard definition of the determinant. I will leave it to you, and this is a good exercise to show that this expression here is identical to this expression here. All right. Now, how do we sample from this distribution? Gaussians is one of those things that is very dry. I'm not going to spend more time in this lecture going over the details of a Gaussian. I strongly recommend you spend some time on the Wikipedia page, like I said, in the Google group today. Because then you can just basically revise all the properties of Gaussians. And then I'm going to give you on Thursday a bunch of exercises that will get you to manipulate Gaussians and learn all about their properties. I will also give you a data set on Thursday so that you start doing some data analysis. A big part of this course is to play with data, so on Thursday we start doing that. Okay, how do we sample from a Gaussian distribution? So we know how to sample from 1D Gaussians. We know that if we have a 1D Gaussian, we know how to draw a sample from a 1D Gaussian. And hence, in particular in machines, we know how to draw samples from a Gaussian that has 0 mean and variance 1. Now, if all we can do is draw random numbers that have 0 mean and variance 1, in order to draw random variables that have mean mu, we essentially draw, if I had y, let's give these guys different names, and y is n01, and I want to draw x, then I would just basically draw x by I draw y, I multiply it times sigma, and then I do a shift. Okay? I'm going to get you to prove this in your homework, that these two expressions are equivalent. But you can sort of, at least the mean should be obvious. If you want to change, if you have random variable center at 0 and you need random variable center at 2, you essentially draw the random variable center at 0 and then you add 2 to shift them. And with the variance, you just need to pay attention to that squared. Now, if you're in the multivariate case, using this derivation that we did before is essentially what's going to be needed. If we need to draw a random vector from a multivariate distribution with mean mu and covariance sigma, we will first break the matrix sigma into the product of two matrices. I'm using the double bar under to indicate that it's a matrix. And this is called the Cholesky decomposition. And we won't really be doing this. The computer will do this for us. I'm just trying to tell you what it is that the computer does so that when you use the computer, you know what that device is doing for you. So that it's not magic numbers coming at you, but you actually understand where they come from. So if you take a course on sparse linear algebra or sort of numerical linear algebra, you learn about this thing called the Cholesky decomposition, which is a way of factoring a matrix into the product of two matrices, which I'm just stating the fact. I'm not going to tell you how to do that. For that, you take a linear algebra class. But if you have that, that's essentially the equivalent of taking the square. And we will be able to draw this vector by simply adding a vector to the matrix B times Gaussian variables n 0, 1. Now, if I know how to draw this guy, if I know how to draw the 1D Gaussian variables, then using the previous derivation, I know how to draw these variables. Because essentially, if I want to draw n variables, I would just draw n 1D variables. And once I have n 1D variables, I multiply them times the matrix B, and I add to it the vector mu, and that's my random vector, my Gaussian random vector, multivariate Gaussian vector. Okay, so that's just to give you an idea of what the details are of how MATLAB gives you those random vectors, those Gaussian random vectors.
In all sigmas, we broke into that square form.
Yes, because as long as the sigmas are what people call symmetric positive definite matrices, they have positive eigenvalues. Which they have to, because a Gaussian, if a Gaussian didn't have that property, it would kind of implode on itself. It would no longer be a bell. Okay, so that's how computers generate random numbers. And the process of learning from data is essentially going from samples that you see in the real world, samples of images, samples of things that people do, to a model. In this case, I'm using this Gaussian model, which at this point, admittedly, is a bit abstract, but hopefully when I start doing linear regression, it will be a bit more concrete. And then the process of imagining is the opposite, is you have that model and you generate samples. And like I said, and hopefully convinced you in the first lecture with those videos, that if you can imagine the world, and the world is as you imagined it in your predictions, that means that you kind of have learned about, you understand the world. Okay? If you happen to be one of the unfortunate people that have extreme forms of schizophrenia, you will be imagining, and you will not know whether you're imagining from whether the signal is coming from your senses or from your imagination. And so you'll start seeing a reality that isn't there. And that's common in most of us. So understanding learning is essentially a big part of understanding the human condition, and also a big part of making moves toward designing drugs to help people with mental disability. All right, let's be a bit more now concrete to what I mean by learning. We're using probability. Let's now assume that I have 3 data points, and these will be scalar data points, and essentially they're 3 points, 1, 0.5, and 1.5, and those are the points that I've shown here in these 2 alternatives at the bottom. So they happen to be, oh wow. I'm going to use this one. They happen to be the blue points in the nice projector. Now, I'm going to assume, and here comes the big assumption, I'm going to assume that these points come from a Gaussian distribution. That's my model for the data. They may or may not, but for now, let's assume that they do come from a Gaussian distribution. And let's assume that I do know that the variance is 1, so there's no uncertainty there. But I don't know what the mean is. What's the mean that best describes those 3 points? Now, we obviously know that to get the mean, the expected value, a good estimate is just to add those 3 numbers and divide by 3, which would give us, 1. Okay, so that's the... but where does that come from? Where does that rule come from? That's what we're going to go over now. Let's assume that I have 2 guesses at theta. So 2 different people gave me 2 guesses. One person told me 1, and another person said, no, I think theta should be 2.5. How many of you would pick theta equal to 2.5? Theta equal to 1. Okay, one of the people with the hand up. Why? That's correct. And by likely, I mean this, and I think she means this green bar is taller. If the 3 points are independent, in order to compute the joint probability, we just multiply the 3 green bars. In the model on the left, the product of those 3 green bars will be bigger than the product of these 3 green bars on the right. And so that's why we prefer that model over there. This distribution, P of x given theta, or sorry, P of y given theta in this case, is what we call the likelihood. It's the probability of the data given the model. The model in this case is Once you know the parameters, that's your model. Okay. Out of two alternatives, the one that makes the data more probable, in other words, the one that explains the data better, is the one that we choose. That's essentially the principle of maximum likelihood, which I will formalize soon, but that sort of gives you the intuition. Okay, now how do we do linear regression? So in the last class, we learned that to do linear regression, we would take if we had several points and we want to do linear regression, we essentially fit a line through those points. And then the goal was to minimize these quadratic distances. So in other words, minimize y minus x times theta transpose y minus x theta over theta. And then we said that the solution was x transpose x inverse x transpose y. So provided that you knew how to form the matrices x and y, computing theta was a trivial thing. And that guaranteed that we minimize these squared distances, which is equivalent, if I rewrite this, as minimizing the sum from I equal 1 to n, where in this case n is equal to the number of points, which is 6, yi minus xi transpose theta. So on the probabilistic perspective, on the other hand, we simply assume that the y's will be distributed according to a Gaussian distribution. Okay? That each y is Gaussian, and that the mean happens to be the line. In other words, x transpose theta. And we will assume that those points will have a variance. They vary about the line. So the line will be the mean, and the points will vary about that line. Saying that is essentially, in math, is the same as saying that the mean is x transpose theta and that the variance is sigma squared. The joint distribution of the vector, of the n components of the vector y, if we assume that those points are all independent, it's just the products of the probabilities of each point. And each point we're assuming is Gaussian, with mean xi theta and variance sigma squared. Now, if I take a product of a constant to a power n times, I just basically get the constant to the power n. And if I take the product of an exponential n times, I just get the exponential to the sum over n of the exponents, just using the properties of exponentials. You know, e to the a times e to the b equal e to the a plus b. Now, we see that now this distribution is starting to look a lot like this minus the typo. So the distribution, the exponent, is starting to look a lot like the error function that we try to minimize. So maximizing that probability will be equivalent, as we'll see, as minimizing this cost function. Minimizing a cost function is the same as maximizing a probability. So that's sort of very important, and that's a common theme throughout all the models. And now I can do the same thing. I can rewrite everything in matrix vector notation. Instead of writing it as a sum of squares, I can group terms, and I can essentially get something that looks more like the second term that we had in the last class. Okay. Now, what's the picture? The picture is still the one of linear regression. So we still have a variable y, an input variable x, we have many points. We fit a line that goes through those points. The line has a slope and an intercept. And each point xi has height yi. The prediction is yi hat, which is xi transpose theta, which is the mean. And to say that each point is Gaussian distributed is just saying that there is a Gaussian distribution whose mean is centered at, so the mean essentially is equal to yi hat. And that has a variance sigma squared. So each point is distributed according to a Gaussian. And the distribution is on the y direction. Because we talked about the probability of y, not the probability of x. X is assumed no. Some notation, actually, as we're introducing notation, this bar here means given. So the quantities on the right are given. Because typically in linear regression, someone gives you an x and you have to predict the y. So your uncertainty in predicting is in the y, not the x. The x is usually given to you, so you observe. Go ahead.
So let's say there's a certain measurement that you believe it more or less. Then you're just going to use a weighting matrix?
That you believe it more or less. You mean a measurement x or a measurement in y?
Y.
In y. This is kind of what we're saying here. We're saying that I believe this y comes from that Gaussian. But I'm not saying that it's centered at the line. I'm not saying that I know precisely what it is. All I'm saying is that it comes from that Gaussian. So when I say that, I'm basically, if I understand your question well, I'm saying it's most likely to be, say, in that interval.
No, but in the process when you're, for example, doing the least square, so you're estimating this, the mean and the variance.
Yeah.
And let's say you have some sort of prior knowledge if a certain measurement is more or less likely to be accurate. Then how you
yes. Okay. Yeah. So I might know that some of xi's will have lower variance than others.
Right.
In which case I would have a different variance. Yeah, so you could do that very easily. So I'm going to do the case where the variance is the same for all the points, and I'm going to leave the other one, as I often do, for the exam. You'll see that
Question.
by the time the exam comes, if you've attended these lectures, you'll know the questions.
Would your assumption of the distribution of y affect the maximized functional you end up with?
Yes. I'm picking the distribution. By choosing the distribution, I have made a strong commitment to what I believe the model is. But here is the thing. If you know how a Gaussian distribution works, you'll know how a Kalman filter works. How many people know what a Kalman filter is? If you fly an aircraft, it would crash if you don't know.
We'd just like to make an announcement, if that's okay with you, for the Thunderbolts UBC team.
How long will you take?
Just a few minutes, maybe 2-3 minutes. That's okay, or we can come back another time.
Yeah, the class ends at... Can you come back in 20 minutes?
Okay.
Thank you.
Thank you.
Okay, so in 20 minutes, remind me that he needs to make an announcement. We should be done. And that completely... Aircraft. They use common filters to land. The cars that drive by themselves, they use common filters. What are common filters? They're just the mechanisms that take two Gaussians, multiply them, or collapse Gaussians. They're just Gaussian manipulations. And most of the algorithms we use for many things are just Gaussian manipulations. I've talked about Gaussians over scalars, univariate Gaussians. I've talked about Gaussians over vectors, multivariate Gaussians. And next week I'm going to talk about Gaussians over functions. Once you understand Gaussian over functions, we'll be able to actually come up with some very powerful optimization algorithms that could lead to like massive changes in automation in the world over the next few years. And so as of next week, I'm going to start just in a week and a half. I'll be able to run by you a bunch of project ideas of things that haven't been done yet and that you could do just by understanding what a Gaussian is. A Gaussian is a super cool distribution, very general. Okay. And of course, each point, I forgot to say that, but essentially each point is assumed to be Gaussian distributed. So there is a Gaussian for each of these points. And so the process of learning, just like before, is just the process of maximizing these green bars. So just like in this previous game where we tried to maximize the height of these green bars, linear regression is all about changing the slope of that line to maximize the height of those green bars. And maximizing the height of those green bars is the same as minimizing the spring lengths.
In this case, if we assume all the y's are uniformly distributed, but I have a feeling that
if you were to assume that they were uniformly distributed, you'd basically be assuming that there's a distribution somewhere like this.
Yeah. And I have a feeling that even if with a uniform distribution assumptions, we will get a line like this, which is
You'll get a pretty good line. In fact, that line is going to be more robust to outliers. So you could do this linear regression with many distributions. For now, I'm trying to teach you how to do it with a Gaussian. But you're absolutely right.
Would the results be the same?
No, it's not going to be the same. Depending on which distribution you use, you'll get different results. So here is one thing that people... I'm going to take a break and sort of go over. And here's one interesting case. Suppose you have points that look like this. Okay. Now, this is very common. You're measuring a flow meter somewhere up in northern BC, and that's being transmitted through, the height of the water is being transmitted through a satellite link back to, a place in Surrey where they're doing all the data analysis, and they're trying to basically decide when to open the gates of a dam or not. They're trying to avoid the water from fluctuating, because when the water fluctuates, basically if it goes up too quickly, the little fish go to the shore, and then if it goes down too quickly again, then the little fish get caught in the puddles, and then the little fish die, and as a result, the amount of nice fish that we get in our restaurants in Vancouver goes down, or the price goes up. So this is actually a realistic case. I've done consulting on this kind of stuff. What happens there sometimes is that these measurements get corrupted, either in the satellite link or the sensor gets stuck, and then of course it's very expensive to send someone to repair, and you just have to live with it. The data is going to be dirty and it's going to have these guys, outliers. Now, if you want to do some sort of fit a model to do some sort of prediction, you ideally would like to fit a model that does this. But here is the catch. Because errors are measured in terms of vertical distances, this error is going to dominate. This is going to be a huge number because it's squared. So it would be, let's call this point y3. And so this height here is y3 hat. y3 minus the prediction squared is going to be a large number. So that spring is going to really pull the line. And so when you learn, you will, instead of learning this beautiful line, we end up learning the green line, which is, I've exaggerated it a bit, but it's going to be off what you would want. So in this case, what's really screwing us is this Gaussian assumption, equivalently the squared assumption. So by assuming a Gaussian on this point, I'm placing a probability distribution and as I mentioned, the center would be mu, but because it's an exponential, the Gaussian is an exponential, it means that this height is decaying exponentially. So this green bar here is exponentially small. Now, when I multiply all the green bars, this green bar here will be almost 0. So when I multiply all the green bars times that green bar, it's going to give me a very low probability solution. So the way that the model will try to fix this is by going for the green line, tilting the green line, in which case we get a very bad prediction. How can we fix this? We get rid of the Gaussian. And we introduce a different kind of distribution. So I'm not going to tell you which distribution, but typically what we would use is something that we call a t-distribution. And without defining it, it looks like this. It's a distribution that the tail doesn't decay exponentially. It doesn't decay as fast as a Gaussian. So if a point is out here, it will still have some probability. So that number is not going to be close to 0 and cause underflow or cause any other sort of trouble. And then we will still be able to get a line that is close to the black line. So in some cases, it will be important to move away from the Gaussian distribution, like in this case of outliers. But before we move away and I introduce all the formulas for the t-distribution and so on, let's stick with the Gaussian and proceed to derive the maximum likelihood estimates of the Gaussian. Once we know how to do the Gaussian, it will be easy to do other distributions. Okay, so the idea of the maximum likelihood estimate then is for a Gaussian in linear regression is we just maximize this probability, or equivalently, we maximize the log of that probability. And the reason why we take logs is because it's a lot easier to work in log space. We get rid of the exponent. So in particular, we're going to define this quantity called the log likelihood, which is going to be to minus n over 2 log of 2 pi sigma squared minus 1 over 2 sigma squared y minus x theta transpose y minus x theta. Instead of maximizing the probability, we maximize its log. And the two are the same because the log is a monotonic function. So it doesn't change the location of the maximum. Now, if we write the likelihood like that, and let me write it again here. So L of theta is equal to minus n over 2 log of 2 pi sigma squared in order to find where the peak is of the Gaussian, in other words, in order to find where this peak is, we just essentially differentiate and equate to 0 and see where the slope is 0. And so the derivative of the log likelihood with respect to the vector theta then is just equal to 0 minus 1 over 2 sigma squared. And now note the derivative of this guy is just a derivative that we did in the last class, because that's just a quadratic least squares. So I'm going to do it quickly. So that would be 0 minus 2. Let's see if I can do it by heart. I do these things all the time. X transpose Y. And I've written that quickly because I've done this a million times. You can go over it in your own time. We did it in the last class slowly. And now if we equate to 0, we get theta is equal to X transpose X. Okay. So no surprise. The theta maximum likelihood, I'm going to put an ML there to indicate that it's the maximum likelihood. The theta maximum likelihood is the same as the theta least squares, because the negative log of a Gaussian is just the quadratic function. Oh yeah. I knew the answer, so I was working back in my head. Likewise, we can compute the derivative with respect to sigma to get the maximum likelihood estimate of sigma. So now we start seeing something much more general than with going with the cost functions. A Gaussian makes sense. We can describe its shape, and now it has more parameters. And so when the question comes in, how do we get these other parameters, the variance, which is something we didn't talk about. How do we talk about the uncertainty of these points? And uncertainty is very important. It's important, and I've used this example before with these guys, it's important that I tell him, your test is positive. The probability that you will die is 1. As opposed to saying the probability, 1 plus or minus 0.01, as opposed to saying the probability is 1 plus or minus 1. Okay, so in one case, I'm basically saying something that is nothing, because there's too much variance. In the other case, I'm very certain. So knowing uncertainty, quantifying risk is really important. And that's why most of finance, in fact, in Wall Street, is all, most of the departments are just called risk management. It's all about understanding variance. So knowing the spread of this point is really important. And sometimes in finance, it's actually more important than actually where the line is. How do we get this? We have an expression for the likelihood of sigma. So we just take the derivative with respect to sigma of the likelihood of sigma. And if you do this, you will get that sigma squared is equal to this. It's a standard estimate of the variance. Basically, the random variable minus the mean squared. And please do this, because you will see it again. Now, once we've done that, once we have the estimates of theta and sigma, we have the likelihood. We have recovered the Gaussian. We know the shape of the Gaussian distribution. We know its mean and we know its covariance. And if we know its mean and its covariance, in order to make a prediction, in the training set, from the training set we got the theta ml and the sigma ml. And once you have those, then you just plug those in the Gaussian, and that gives you the prediction. So if you have a new point, x star, in order to predict, you essentially use the mean, which is x star transpose theta. And then you also know how certain you are that that's what the prediction should be, because you also have estimated sigma, and sigma gives you an estimate of the uncertainty. This is not, as we will see in a week and a half, this estimate of uncertainty is actually not very good, but we will learn another estimate that's very useful, and that will allow us to do all sorts of very interesting active learning. Okay, to summarize, maximum likelihood learning is part of something called frequentist learning. It's based on frequencies. So as we've kind of seen here, this is just the estimator of the variance is just essentially the counts. If n goes to infinity, that becomes the expectation, which is the true variance of the model. And so the assumption here is that there is one truth, and such that if you were to get more and more data, you would be able to recover that truth. There is this one model that has a true parameter theta naught that produced the data, and what your game is, given a finite set of data, you're trying to guess what that theta naught is. And you call that theta naught theta hat, as we've been doing. And so in maximum likelihood, we're essentially finding that theta hat by maximizing a joint probability, the probability of the data given the thetas. Now, in order to understand a maximum likelihood, it's useful to introduce a much simpler model. So we've seen the Gaussian. Another distribution that's very useful to know is the Bernoulli, because the Bernoulli, as some of you already know, is a great model to talk about text, to talk about words, and to talk about things on the web. And certainly that's how we will use it later on. Now, a Bernoulli model describes a coin or an event or something that's either true or false. So it will allow us to do all sorts of logical statements. The Bernoulli distribution has the following shape, essentially this here. The probability that the coin is 1 is theta. The probability that it's 0 is 1 minus theta. And then when you add up the two, you should get 1, so that it's a valid probability. So in other words, it's a binary distribution like this. And then this height is 1 minus theta. Okay. We will succinctly write this as p of x given theta equal to theta to the x times 1 minus theta to the 1 minus x. Okay? Because this will be equal to theta when x is equal to 1, and this will be equal to 1 minus theta when x is equal to 0. Okay, because one exponent will be 0 when the other exponent is 1. Now, I'm going to define an important concept to talk about uncertainty called the entropy. The entropy is just a concept that was introduced by Shannon. It's the sort of, how many of you have done information theory? Okay, engineering or CS? CS, okay. Glad to hear that some of you still, in some places, it's still being taught. So modern computers essentially were built on the theory of Shannon to a large extent, at least our communication networks and so on. Entropy is a measure of uncertainty, and is what's used to quantify uncertainty of transmitting bits over channels. The Wikipedia page will tell you lots of things about entropy. Right now, all I need is to tell you what the expression is, and to tell you that if I have a Bernoulli random variable, the entropy is just minus the sum over x being either 0 or 1. And then I'm going to write this whole expression here. So I have theta to the x times 1 minus theta to the x times the log of theta to the x times 1 minus theta to the x. Which is 1 minus x here, which is 1 minus theta times the log of 1 minus theta plus theta times the log of theta. And if you plot this quantity, it looks like that. So recall that p of x equal 1 is just theta. The entropy for a coin is such that when the coin is completely unbiased, when I have a fair coin has the highest entropy. And it just means that if I have a perfectly fair coin, you will have no clue whether it's going to, well, you'll know that only with probability of half, it will either be tails or heads. But if I tell you that the coin has high probability of being tails, in other words, this is the biased coin, and it has 9%, 90% probability of it being tails, then if I'm going to flip it, you have less uncertainty. You're kind of certain that it's going to be, its bias is going to fall in your favor. And so that's essentially what entropy measures. It measures that uncertainty that you have about the problem. If you don't know anything, you'll have high entropy, and otherwise. Now, entropy is the opposite of information. And in fact, that's how Shannon defined information. The concept of information that we use mostly in English essentially is that. It's the opposite of entropy. You have more information when the coin is biased, when you know exactly what's going to happen. And if there's more uncertainty, more randomness, you have less information.
You're missing one minus in that expression.
Quite likely. Theta. 1 minus theta times log of 1 minus theta. And then, I'm missing 2 minuses. Thank you. Okay, so in the next class, I will finish. I'm going to let these guys have some. These guys want to tell you something about their competition. So I'm going to finish this lecture at the beginning of the next class. But now that we understand entropy, which is uncertainty, I will do a little derivation that will show that maximum likelihood learning is really a process of minimizing your uncertainty about the world. Okay? And the two essentially are equivalent. Whether you approach the problem from information theory or from the process of imagining and comparing what you imagine against what you see, or whether maximizing probabilities, it will always lead to the same thing, which is maximum likelihood. Which is a really powerful concept. All right, go ahead.